Hello, fellow viewer! We are the 11th EMD students of Siliman University, but under the course of General Mathematics, we are the Group 4. Before proceeding, however, to this video tutorial, let us first know who are the members of the 4th group.
Here are the members: Jess Ardonia, Cedric Birao, Joshua Marquez, Dave Obdamin, Pierre Renasha, Sinay Katolabing, and yours truly, Nimrod Ko. So let's begin.
Solving logarithmic inequalities. A logarithmic inequality is an inequality involving logarithms. In our tutorial, we have 9 parts. The first 2 slides will tackle about properties and strategies, while the rest are examples of logarithmic inequalities with solutions on how to solve the problems.
The logarithm of x to the base b is greater than 1. The logarithm of y to the base b then is greater than y. If 0 is less than 1 and the logarithm of x to the base b is less than the logarithm of y to the base b, then it is greater than y. If 0 is less than 1 and the logarithm of x to the base b is greater than the logarithm of y to the base b, then x is less than y. Note, the properties also hold when less than is replaced by less than or equal to, and greater than is replaced by greater than or equal to. Since logarithm is defined for positive real numbers only, then x is greater than 0 and y is greater than 0.
Strategies when dealing logarithmic inequalities. 1. Ensure that the logarithms are defined. Logarithm is defined for positive real numbers only. That is, x is greater than 0 and y is greater than 0. In other words, we find the domain. Number 2. Ensure that the inequality is satisfied. When b is greater than 1, retain the inequality symbol, and when b is greater than 0 and less than 1, reverse the inequality symbol. And lastly, find the solution set. The solution set is the intersection of the solutions obtained in step 1 and step 2. Take note that these are only some of the strategies when dealing with logarithmic inequalities, and you can use other ways that would work best for you.
So hi guys, let us now proceed to our example 1. Okay. So example 1, let us solve this equation. So log base 2 times 2x plus 1 is greater than log base 2 times x plus 3. So first, let us ensure that the logarithms are satisfied. So 2x plus 1 is greater than 0 to 2x is greater than negative 1 to 2x is greater than negative 1/2 or negative 1/2 to infinity. Then we will simplify it to x plus 3 is greater than 0 to x is greater than negative 3 or negative 3 to infinity. So our intersections are negative 1/2 to infinity union of negative 3 to infinity, which equals to 1/2 to infinity. So let us not stop there. We should also ensure the inequality is satisfied. As we all know, the base of b is 2, which is greater than 1. This implies that the inequality symbol is retained. So let us proceed to 2x plus 1 is greater than x plus 3. We will transpose the following numbers, which will turn out to negative, the 1 to the right side and the x variable to the left side. So both will be negative. So 2x minus x is greater than 3 minus 1. We will simplify it. We'll put the variables together, so it will result to x is greater than 2 or 2 to infinity, which our intersection results to negative 1/2 to infinity under union of 2 to infinity, which equals to 2 to infinity. Therefore, the solution is x greater than 2 or 2 to infinity. Thank you.
Example number 2. Logarithm of x squared to the base 2, x plus 1 greater than logarithm of x squared to the base 4, x squared. Here the bases are different, but they are related to the fact that 4 is equal to 2 squared. Rewriting the inequalities to use 4 as base give. Logarithm of x squared to the base 4 is x plus 1 to the power of squared greater than logarithm of x squared to the base 4. Ensure that the logarithms are satisfied. X plus 1 greater than 0, x minus negative 1, or negative 1 positive infinity. X squared greater than 0, x greater than 0 or 0 positive infinity. Intersection. Negative 1 positive infinity and 0 positive infinity equals equal to 0 positive infinity. Ensure that the inequality is satisfied. X plus the power of squared greater than x squared. X squared plus 2x plus 1 greater than x squared. 2x plus 1 greater than 0. 2x greater than negative 1. X greater than negative 1 half or negative 1 half positive infinity. Intersection 0 positive infinity and negative 1 half positive infinity equals to 0 positive infinity. Therefore, the final solution set is 0 positive infinity or x greater than 0.
Example number 3. Solve the equation log of quantity x plus 6 base 7 is greater than log of quantity x plus 6 base 5. In this case, we have to use the change of base property, which says that log of x base b is equal to log of x base a divided by log of b base a. And so we are able to get log of quantity x plus 6 divided by log of 7 is greater than log of quantity x plus 6 divided by log of 5. After this, we apply cross multiplication, and so we are able to get log of 5 times log of quantity x plus 6 is greater than log of 7 times log of quantity x plus 6. Evaluate and we will have the result of the quantity of log of 5 minus log of 7 times log of quantity x plus 6 is greater than 0. Since log of 5 minus log of 7 is a negative number, log of quantity x plus 6 must also be negative. Otherwise, the product will result to a negative number. Therefore, log of quantity x plus 6 is less than 0. In this situation, we need to express 0 as a logarithm. Therefore, we apply the logarithm of the base rule, which says that log of a base a is equal to 1. Therefore, we are able to get log of quantity x plus 6 is less than 0 times log of 10. Evaluate. Log of quantity x plus 6 is less than 0 times log of 10 raised to the power 0. As we all know, any number that has a 0 for an exponent is automatically given the value of 1. Therefore, log of quantity x plus 6 is less than 0 times log of 1. Since the base is a is equal to 10 greater than 0, we are able to get x plus 6 is less than 1. Evaluate, and we are able to get the value of x is less than negative 5. Checking. First, we need to get the 0 of x, and so x plus 6 is greater than 0. And when we put 6 to the other side, we are able to get the value of x is greater than negative 6. Since we have x is less than negative 5, the solution is x is greater than negative 6 and is less than negative 5. Or in interval notation, x is an element of the set negative 6 and negative 5.
Now we have here the fourth example. The problem is to solve the logarithm of 6x to the base of 2.5 plus the logarithm of 2 to the base of 2.5, which is greater than or equal to the logarithm of 16 plus x to the base of 2.5 plus the logarithm of 4 to the base of 2.5. Now this problem can be condensed further using the laws of logarithm. On the left side, the product rule of logarithm can be applied, which we have to multiply 6x and 2. 6x plus 6x times 2 results to 12x. Now on the right side, the product rule can also be applied, which we get here is that 4 times 16 plus x. Now the first step is to ensure that the logarithms are satisfied. So the first term here we have 12x is greater than 0. By dividing both sides by 12, we get x is greater than 0, or 0 and positive infinity, which is in interval notation. For the second one is 4 times 16 plus x is greater than 0. Now, we have to exclude here number 4, since the term that has x in it is 16 plus x, which is this one. So 16 plus x is greater than 0. And by transposing positive 16 onto the right side, we get negative 16. Hence, the final answer, or the result, is that x is greater than negative 16, or if it's in interval notation, we get here negative 16 and positive infinity. Now, the intersection of 0, positive infinity, and negative 16 and positive infinity is 0 and positive infinity. Intersection, by definition, is that it consists of all the elements that are contained in all of the intervals. Like, imagine the x-axis on the Cartesian plane. The points there are negative 16, 0, and all of the positive integers. Now, the only element that consists in all of the intervals is 0 and positive infinity. Now, the second step is to ensure that the inequality is satisfied. Now, since the base b is equal to 2.5, which is greater than 1, this implies that the inequality symbol is retained, or it's not changed. So, we have here 12x is greater than or equal to 4 times 16 plus x. We multiply this, so we have here 16 times 4 equals 64, and positive x times 4 is positive 4x. Now, 4x is to be transposed onto the left side, so we have here 12x minus 4x is greater than or equal to 64. And 12x minus 4x is equal to 8x. And by dividing both sides by 8, we have x is greater than or equal to 8, or 8 and positive infinity in interval notation. Now, for the intersection of 0 and positive infinity, which was the result of the first step that we have done, and the 8 and positive infinity, which is the result of the second step that we have done, is the 8 and positive infinity, or in other words, it is x and greater than or equal to 8. Therefore, the solution of this problem is 8 and positive infinity, or x is greater than or equal to 8.
Example 5. We need to solve for the logarithm of x minus 3 to the base of 1/2 is less than the logarithm of 2x minus 5 to the base of 1/2. So the base is 1/2, and if you can recall, if the base is in between 0 and 1, we need to reverse the inequality symbol. So it is x minus 3 is greater than 2x minus 5. We cancel the logarithm because they have the same base. So the next thing we need to do is ensure that the logarithms are defined. So x minus 3 is greater than 0 is equal to x greater than 3, or in interval notation, 3 and positive infinity. Next is 2x minus 5 is greater than 0. It is equal to x greater than 5/2, or in interval notation, 5/2 and positive infinity. So the intersection of these both is 5/2 and positive infinity. So the next thing we need to do is to ensure that the inequality is satisfied. So x minus 3 is greater than 2x minus 5. It is equal to 2x at 2 is greater than x, or x is less than 2, or in interval notation, it is negative infinity and 2. Note that 5/2 and positive infinity and interval notation negative infinity and 2 do not intersect, if you can imagine in your mind. So therefore, there is no solution to logarithm of x minus 3 to the base of 1/2 is less than the logarithm of 2x minus 5 to the base of 1/2. And here's the proof. As you can see, the interval notation 5/2 and positive infinity is 5/2 to the right. And as you can see here, the interval notation negative infinity and 2 is 2 to the left, which is to the negative infinity, and it does not intersect with 5 halves and positive infinity, so therefore there is no solution.
Example number 6. Solve log quantity of 2x squared plus 2 is greater than with the base 2 is greater than log x to the power of 4 with base 4. So first step is to ensure that the logarithms are satisfied from the left side of the original equation for the regular equation. We have 2x squared plus 2 greater than 0. Transpose positive 2 on the right side, thus it becomes negative 2 now. Since the left hand side is always positive, the statement is true for any value of x. From the right side of the original equation, we have x to the power of 4 greater than 0 by getting the fourth truth of both sides. The result is x greater than 0 or 0 and positive infinity. In interval notation, the intersection of these two results is that x is an element of real numbers. In this situation, the bases are different but similar. Precisely, we know that 2 squared is equal to 4. So, log the quantity of 2x squared plus 2 with the base 2 is greater than log quantity of x to the power of 4 with the base 2 squared. Applying the rule log m times y with the base of a is equal to 1 over m with log times log y with the base a. So log with the quantity of 2x squared plus 2 with the base 2 is greater than 1/2 log quantity of x to the power of 4 with the base 2. To log 2x squared plus 2 with the base 2 is greater than log x to the power of 4 with the base 2. To log 2x squared plus 2 with the base 2 is greater than log x squared with the base 2. The base is a is greater than 2. A is equal to 2 greater than 1. So we conclude that 2x squared plus 2 is greater than x squared. So we have x squared greater than negative 2 to x element of r. The statement is true for any positive value of x because the power function with an even exponent is always positive or 0. Therefore, in every x element of r is the solution.
Example 7. Log base 8 x minus 3 plus log base 8 x plus 4 less than 1. Ensure that the logarithm are satisfied. X minus 3 greater than 0 to x greater than 3 or 3 positive infinity. X plus 4 greater than to x greater than 0 to x greater than negative 4 or negative 4 positive infinity. Intersection 3 positive infinity intersection negative 4 positive infinity equals to 3 positive infinity. Ensure that the inequality is satisfied. X minus 3, x plus 4 less than 8 with the power of 1, 2x squared plus x minus 12 less than 8 minus x squared plus x minus 20 less than 0, 2x plus 5 x minus 4 less than 0. There are two ways the product AXB can be less than 0. So A less than 0 and B greater than 0, or A greater than 0 and B less than 0. Next, x plus 5 less than 0 to x less than negative 5 and x minus 4 greater than 0 to x greater than 4. And x plus 5 greater than 0 to x greater than negative 5 and x minus 4 less than 0 to x less than 4. Intersection positive negative infinite negative 5 intersection to 4 positive infinite is equals x belongs to empty set, while negative 5 plus positive infinite intersection positive infinite and 4. So equals to x belongs to negative 5 and 4. Intersection negative 5, 4, intersection to 3 Positive infinite is equals to 3 and 4. Therefore, the solution is 3 and 4, or 3 less than x less than 4. So guys, some of our examples are from the internet, and so we provided 3 references in our presentation.
Well, that's it guys. Thank you for listening. Again, the reporters are Jess Ardonia, Cedric Birao, Joshua Marquez, Dave Obdamin, Pierre Inasha, Nimrod Ko, and Shinaika Tulabing, our group leader. And our subject is General Mathematics, and our teacher, Marivic G. Muhidin. Thank you ma'am for a great year, and we will be signing out. Thank you.